Hello and welcome to the second part of this module, which is about estimation theory. In this second part, we will start with an introduction to basic probability theory. We will first of all try to give an intuitive understanding of what probability is and what it isn't, some basic probability theory background, and then the ultimate objective will be to define and understand what is the conditional expectation. The conditional expectation is the key tool that we will be using in estimation theory. So let's talk a little bit about randomness. Here we'll try to understand what randomness is, and to understand also that randomness is difficult to understand. I'll give you 4 facts. The first one is that I rolled the die 50 times, and I obtained the following sequence that I wrote down and I'm presenting to you here. So I got 3, 2, 5, 5, 4, and so on. The magnificent thing with this sequence is that it's absolutely unique. There is no way you can repeat this experiment and replicate my sequence. This is mine, this is my sequence. You can't do the same. Actually, the chance that you will roll a die and you will produce exactly the same sequence is incredibly small. Let's see how small it is. So it's a fact that if 1 billion people were to roll 50 dice every second for about 250 years, they would have a probability of 10 to the minus 20 to produce the same exact sequence. 10 to the minus 20 is a rather small number. Here is another way to look at this to gain some to put things in perspective. If 1 trillion people were to roll 50 dice every millisecond for 25 million years, they would have 1 chance in a million to produce this exact sequence. So it's practically unique. An interesting fact about this is that number 1, the outcome 1, shows up just twice, and we have 50 observations. One would perhaps expect that 1/6 of these 50 should be 1. That's not wrong, but here what happened is that 1 showed up just twice. Why is that? Just because it's a random experiment. Number 2, another interesting fact is the infinite monkey theorem, which is due to the mathematician Borel. So imagine you have an immortal monkey who has been trained to strike on the keys of a typewriter randomly and ceaselessly, day and night, forever. Then after some point, which might be trillions years ahead of our time, it is certain that the monkey will produce the entire works of Shakespeare and any other book without any typos. There is a project called the Library of Babel. It's a virtual library where you can find many of the works of such an infinite monkey. You can find there an incredible number of gibberish generated by a monkey. And the software there gives you the possibility to look up anything you like up to a length of 3,200 characters, 3,200 characters. So anything you type that has at most this length will be found in a book of the Library of Babel. And here's what I did. I copied a passage from What a Piece of Work is a Man of Shakespeare, and I found it in a book in the Library of Babel, and I played around with many other texts. I tried from the literature. I wrote down Pantelis Pasakis is the best lecturer known to humanity. Everything is there. So randomness contains all possible outcomes. In a way, we can say, roughly speaking, that randomness contains everything that is possible. However, although we cannot predict in advance what the outcome of a random experiment will be, we cannot predict when we flip a coin whether it will be heads or tails, we can still observe certain patterns. What you see here is known as Galton's board, also known as a bean board. You drop a bead from the top, it bounces on a peg inside this device. It's a vertical board with pegs. and it bounces and it can go randomly either to the left or to the right, and eventually it will end up in one of these containers at the end. There is absolutely no way to predict where exactly it will end, but one thing we can tell for sure is that if we repeat the experiment with multiple beads multiple times, then more beads will be concentrated in the central compartments and significantly fewer as we move away. And we will be able to observe, if we do the experiment with a large number of beads and with a very tall Galton's board with many layers, we will see that we approximate what is called in statistics, it is the celebrated bell-shaped curve or the normal distribution. We will introduce these things later, but the take-home message here is that we see that the pattern emerges out of randomness. So you cannot predict what one individual ball will do, but you can say things about their population. The last thing that I would like us to show here and discuss is the fact that our intuition is wrong. Your intuition is wrong is a maxim in probability and statistics, and here are just a few examples to convince you that things are so. The simplest one is that you've tossed a coin 10 times, and let's say that you've got 10 heads, 10 in a row, heads, 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 again and again. Then what is the probability that the next one is a head as well? Now some people, I think most people will think, well, it's been 10 times heads, maybe it's high time we saw tails, and people would bet on tails. But that's not true. The probability is 50%. If we have a fair coin, then the probability that the next outcome is a head is 50% and 50% for tails. Some other people might think that it's more likely to see a head again, because this coin seems to have the tendency to produce heads. But again, if it's a fair coin, the probability, I repeat, is 50%. What is the probability in a classroom of 23 students to have any two students who have the same birthday? The probability is surprisingly high, so you wouldn't expect in a classroom to find two of your classmates, including yourself perhaps, who have the same birthday, their birthday on the same day. But if you have 23 students, then the probability is a surprising 50%. So 50% of 23 student classrooms have at least a pair of students with birthday on the same day. The third example is a lot more important, and it goes as follows. A DNA sample was collected from a crime scene and was compared against a database of 50,000 records. The probability of two DNA profiles matching by chance is 1 out of 10,000, so fairly low. Now, a person from that database was identified and charged with murder, and using the only incriminating evidence was that DNA match. But what is really the probability that this match was just by chance? What is the probability that anyone's DNA would give a positive match out of that database? Now the result is a striking 99.3%. So what we need here is a rigorous approach and a rigorous method that will prevent us from doing such mistakes and going into such fallacies. We need a mathematical probability theory, and what we do in mathematics is that we start by stating our axioms and definitions. And we will start by stating Kolmogorov's definition of a probability space. So a probability space is the main concept that we use to model a random experiment. So what is a probability space? It consists of three things. First of all, a sample space, which is a set omega. The sample space is the set of all possible outcomes of the random experiment. So if we flip a coin, the sample space is a set that contains heads and tails. If we roll a die, the set omega, the sample space, contains 1, 2, 3, 4, 5, 6. So that's the first ingredient of a probability space. The second one is the set of events F calligraphic, which is known as a sigma algebra, the sigma algebra of the probability space. This is a subset of the power set of omega. It is, in other words, to put it simply, it is a collection of some of the sets of some of the subsets of our sample space. And the third ingredient is the probability itself. So the probability is a function that you give an event and returns a number from 0 to 1. Let's give one more example. Let's say we're interested in the temperature tomorrow. We don't know that. We have to wait and observe it. Now the temperature is a real number. Let's say, okay, from, let's say, minus 273, which is absolute 0, to 100 Celsius, something very large. So the temperature in our city tomorrow will be certainly somewhere inside there. This is our sample space omega. Now let's pick an event out of that set omega. Let's talk about the event that the temperature is from 10 Celsius to 20 Celsius. So the event is the interval 10 to 20. The probability is a function that takes, for example, this set 10 to 20 and returns a number from 0 to 1. In everyday life, we used to talk about probabilities in percentages. So we have a 50-60% probability. In mathematics, we prefer numbers from 0 to 1. 0 is 0%, 1 is 100%. Now, a probability, we don't know exactly really now what is the probability that tomorrow the temperature will be from 10 to 20. But whatever it is, whatever probability you assign to that event, it must satisfy three essential axioms. The first one is that the probability of nothing happening is 0, and that the probability of anything happening is 1. So the probability of not having any temperature tomorrow, if that makes sense, is 0. This is unlikely. And the probability of having a temperature between 273 and 100 Celsius is apparently 1, or 100%. The second requirement or axiom is that if an event A is a subset of an event B, then the probability of A is not larger than the probability of B. For example, the probability that the temperature is between 10 and 20 Celsius cannot be larger than the probability of the temperature being between 0 and 50. Why is that? Because the set from 0 to 50 is a superset and contains the set from 10 to 20. The third axiom is that if we have a sequence of mutually disjoint sets, then the probability of their union is the sum of their probabilities. So if we have the sets A1, A2, A3, and so on, which are disjoint mutually, this means that there is no element that is simultaneously in A1 and A2. A1 and A2 don't overlap. A1 and A3 don't overlap. A2 and A3 don't have any common elements. They are mutually disjoint. So if that's the case, then the probability of the union of these sets is exactly equal to the sum of the individual probabilities, sum of probabilities of the sets AI. We talked about the collection of all events, and we said that this is called the sigma algebra. Now, a sigma algebra must satisfy certain axioms that deem it meaningful to avoid certain paradoxical cases. A sigma algebra must satisfy these three conditions. I believe this is quite mathematical and it is a formality. So if you like, have a look at the definition, but it will not be essential for what follows. I just felt it should be here for the sake of completeness. So it is a collection. A sigma algebra is a collection of subsets of omega. This is what we need to keep in mind, that this collection satisfies three properties. Let's give an example to better understand what is a probability space and how to use it to model the random experiment of rolling a die. So consider we have a fair die, so no outcome is more likely than any other. What is the sample space? The sample space is the set omega, which is equal to 1, 2, 3, 4, 5, 6. Suppose that the events we have, the events we're talking about, is the power set of omega. What does this mean? It means that we're saying that it makes sense to talk about any outcomes of this die. For example, 2 and 5 is an element of this sigma algebra. 2 and 5 is an event. It is meaningful to talk about the probability that we roll a die and it turns out to be either a 2 or a 5. There is the empty set always must be inside the sigma algebra, and omega is also in the sigma algebra, so it makes sense to talk about what is the probability that we roll a die and it turns out to be 1 or 2 or 3 or 4 or 5 or 6 and so on. We define now the probability P to be a probability that satisfies this property. The probability of any single outcome, like the probability of 1, the probability of 2, 3, 4, 5, 6 and so on, is exactly 1 out of 6. And having defined the probability of these elementary events, the event that we roll a die and we see a 4, for example, is, as we said, 1/6. Then we can compute more complicated, so to speak, probabilities. So since we know that the probability of rolling a 1 is 1/6, we can ask what is the probability of rolling either 1 or 4. So the probability of rolling either 1 or 4 is denoted like this: P, probability of the set that contains 1 and 4. We can break down the set 1 and 4 into two sets. We can write that this is the union of the set that contains 1 and the set that contains 4. And since the probability of the union is the sum of probabilities if the events are disjoint, so there is no common element inside the first and the second set, then the sum of probabilities is 1/6 plus 1/6 is 1/3. So let's put everything together and have a look once again. The experiment we have is the roll of a fair die. The sample space is omega, 1, 2, 3, 4, 5, 6. The sigma algebra is all possible subsets of omega. For example, all these subsets you see here are contained in the sigma algebra, like 1, 4, 5 is contained in the sigma algebra. And the probability is a function to which you provide a set from F and returns to you a number. And it is defined here in such a way that the probability of any single outcome of the die is 1/6. Then we can determine, of course, the probability of any event A in the sigma algebra. Here is the first exercise you can try. You can prove that the probability of the complement of an event is 1 minus the probability of the event. So P of the complement of A is 1 minus P of A. And what is the complement? The complement is all the elements in omega that are not in A. And to understand what this means, you can go to the second question that asks, using the above property, determine the probability of rolling a fair die and not getting 6. Then prove this inequality, that the probability of the intersection is not larger than the minimum between P of A and P of B, that the probability of the union is equal to PA plus PB minus P of the intersection. This one will be slightly more involved, but not too difficult. And the last one is that suppose you have some sets A, 1, 2, 3, 4 up to AN that are mutually disjoint and they make up omega in the sense that their union is omega. when we have such a collection of sets, we say that this is a partition of omega. It is like you segment omega in separate regions. It's like you have a map of a continent and you segment it into countries. Then for every set B that is an event, you have that the set B, the probability of the set B, can be written as the sum of the probabilities of B intersected with AI. Now, having defined the probability space, which is the basic concept in our discussion and in what follows, we can talk about random variables. So a random variable, roughly speaking, is a numerical outcome of a random experiment. So for example, you place a bet. You say if you roll a 6, you win £10. If you roll 1, you lose £100. Otherwise, you don't win anything. So what is a random variable? It is a mapping from the probability space, from the sample space omega in particular, to the real numbers. X of omega is, we say, £10 if omega is a 6, minus £100 if omega is 1, and £0 in any other case. So it is a function, a random variable is a function x of omega. And we will be talking about real valued function. So it takes an element of omega and returns a real number. Now, what is omega? We cannot answer that. It's a random experiment. We don't know what omega is, but we know that if a certain omega does happen, then we will have a certain outcome x of omega. The idea is that nature somehow, or some malevolent guy, chooses omega, and we cannot look behind the curtain and know how they choose omega. They provide it to x, so x is the interface between the unknown part of the world and the observable part of the world, and we observe x of omega. So now, in general, how do we construct random variables? Certainly we need a probability space, omega, f, and p, a sample space, a sigma algebra, and a probability. But we also need a measurable space, which is, in our case, what we talked about before. The real numbers is a measurable space. What is a measurable space? It is a pair of a sample space and a sigma algebra. And what is a random variable? It is a function from omega to e. So from omega to for example, the real numbers. There is a formal definition of what a random variable is. I'm stating here the definition again for completeness, but you can proceed without necessarily knowing this definition. I'm going to just state it for completeness if you want to look deeper into the technicalities of probability theory. So a random variable is such a function, as we said above, that inverts all those sets B of the sigma algebra E calligraphic into elements of the sigma algebra of the original probability space. So x minus 1 of B is in F for all B that are in E calligraphic. It inverts the sets of E calligraphic to the sets of F calligraphic. But that is a technicality that, if you like, you can omit. The important thing to keep here in mind is that a random variable is a function from omega, behind the curtain, to a set E, like the real numbers in front of the curtain, the observable universe. Now suppose that you place a bet and your winnings are as follows. You earn £1 if the outcome is 1 or 3 or 5, and you earn £2 if the outcome is 2 or 4 or 6. You see, we're talking about games and gambling here. That's because of the history and tradition of probability theory. It all came from the study of such random games and gambling. So people wanted to know what they can do to win in gambling, the answer is you can't do anything usually. And at least you want to know the probability that you will win something, or the probability that you will lose, and how much should you expect to win or lose, and so on. So now, what is the probability that your winnings are £2? We're asking now, what is the probability that a certain random variable is equal to a certain value? So what is the probability that x is equal to £2? How do we even interpret that probability? Here is how we define that now. Here is how to understand what we mean when we say what is the probability that x is equal to £2. We can only measure the probability of subsets of omega. So we have to construct such a subset of omega. So that subset we're talking about here is the set of all omega lowercase in big omega, such that x of omega is equal to £2. And what is that set of omega? What is that subset of omega for which it happens that our winnings are £2? It is the set 2, 4, and 6. So it is P of 2, 4, and 6. And what is the probability of that set? If we have a fair die, this is 50%, or 1/2, 0.5. Now, in general, the probability, we define something very useful here, the probability distribution of a random variable. The probability distribution of a random variable is a function f with f uppercase with subscript x that takes a set in the range space of the random variable. So it takes, for example, a subset of the real numbers and returns a number between 0 and 1. It returns a probability. So what is practically the probability distribution of x? It is a function that takes a set B and returns the probability that x is inside B. Once again, it's a function to which you provide B, and it returns to you the probability that your x is inside that set B. And what is the probability that x is inside B? It is the probability of the set of those omega in big omega, such that the outcome x of omega is inside B. It is reasonable, when you have a random experiment, to ask what should you expect from that random experiment. So when you have some random winnings from a bet, how much should you expect to win or lose? Now, suppose you place a bet and you say you agree that if you roll a 6, you win £10. If you roll 1, you lose £100. Otherwise, you win £5. Is that a game from which you should expect to win or lose money, and how much? That's the question. So your winnings are as follows. We construct a random variable following the description above. We say that x of omega is £10 if omega is equal to 6, minus £100 if omega is equal to 1, and plus £5 in any other case. Now the possible values of x are 100, minus 100, and 5. That's the money you can possibly win or lose from that game after playing this game once. Now your expected winnings are defined as follows. The expectation of x, we say, you see that symbol here, E Blackboard face, that's how it's called, E Blackboard face, or the expectation of x, your expected winnings, are given by the sum of x of omega times the probability of that omega. So let's see how we can break this down and understand what it is. It is minus 100, which is the outcome if you roll 1, times the probability of rolling 1, which is 1/6. Plus, now we have to write down the winnings if you roll a 2 times the probability of rolling a 2, plus the winnings if you roll a 3 times the probability of rolling 3, which is you win 5 and the probability is 1/6, plus you see what we're doing here. Now If you roll a 4, you win £5 and the probability is 1/6. If you roll a 5, you win £5 and the probability is 1/6. And if you roll a 6, the winnings are £10 and the probability is 1/6. So you multiply the various winnings with their respective probabilities and then you sum them all up. And if you do the calculation here, you will see that your expected earnings are minus £11.67. So you shouldn't expect to win this game. Maybe it looked like a good deal because you always win £10. You always win £5. In one case you win double, you win £10. But if you roll the unlucky 1, you lose £100. So that's not a good deal. You should expect to lose £11 from this game. In the case where omega is the space of natural numbers, for example, so if it is not finite, it is countable, but it is infinite. It is 1, 2, 3, 4, 5 up to infinity, unbounded. And we have a random variable x that is a function from omega to r, and this is a random variable. Then we can of course define the expectation absolutely analogously. So instead of having a finite sum from 1 to 6, we have a series from 1 to infinity, but the definition is the same. It is that you sum up the product between the outcome of the random variable x of omega, your winnings if omega happens, times the probability that omega does happen. So let's give an example. Let's take a random probability space. Let's take a probability space which is equal to n, the natural numbers, and the probability of number k happening is equal to lambda to the power k times exponential minus lambda divided by k factorial. You can confirm for yourselves that the probability of the set n is equal to 1, or in other words, the sum of all these probabilities sums up to 1. Here lambda is a positive constant. Suppose that the outcome x of k is equal to k. So to put it and to give a practical example here, suppose that you have a computer that spits out natural numbers, and if you get a 5, you earn £5. If the computer returns a 6, you earn £6. If it returns a million, you win £1 million. So it sounds like a very good deal. But how much money exactly should you expect to get from that game? The answer is simply the expectation of your winnings, the expectation of x, and x of k is k. That's what we described here. If the computer spits out k, you earn exactly k in pounds. Then the expectation of that x is the sum of the outcome, x of k, times the probability of k happening. So it is the sum over all k that belongs to the natural numbers, k times the probability of k, which is lambda to the power k, exponential of minus lambda, divided by k factorial. And if you do the math here and you take some time, it's not very difficult, it's just a couple of lines. Take a piece of paper and you try this out, you will see that you should expect to earn exactly lambda pounds. Here is an exercise you can try for yourselves. So suppose you flip a coin twice. If you get the same outcome, 2 heads or 2 tails, we earn £1. If we get opposite outcomes, a head and a tail, we lose 50 pence. First of all, I want you to model this experiment by writing down an appropriate probability space and a random variable, and then determine the expected earnings from that outcome. Note that you flip a coin twice, so what are the possible outcomes? This is what you have to think. So that was an introduction to probability theory in general. In the next video lecture, we will talk about probability densities. And the reason why we need to do that is that so far we have only given examples and we have talked about sample spaces that are either finite, like the sample space of a coin, heads or tails, so we have only two possible outcomes, or the sample space of a die, 1, 2, 3, 4, 5, 6, it is again finite. We have given one example where the sample space was infinite but countable, so 1, 2, 3, 4, 5, 6, but still we haven't given any examples where the sample space would be, for example, the real line or the positive real numbers, as it is the case when we study continuous variables such as temperatures, pressures, voltages, and so on. There the outcomes are not quantized, so to speak. So that's why we need to introduce the concept of a probability density. So for now, thank you very much for watching, and goodbye.